So let's understand a very interesting concept here, which is called as consistent hashing. We'll understand this using an example. Let's say this is a server right here and it's getting 100k requests in a second. Now this might mean that this server is overload. So what's the common solution to it? So we'll have more servers like these to handle this problem. So that is what is shown here in the diagram. These are 100k requests and those get distributed to server number 1, server number 2 and server number 3 right here. But wait, these requests that you see here, 100k requests, these come from different sources or different devices, let's say. These are users, small users here. Now how will these users know which server to go to? So in order to solve this problem, we'll obviously need an entity right here which will distribute the incoming requests into these different servers. So let's update our diagram accordingly. So here I have adjusted the diagram right here. We have these 100k requests coming in. We'll add something called as load manager. Let's name it load manager, which manages the incoming load. Now this load manager distributes the incoming 100k requests into server 1, server 2 and server 3, for example. Looks like we have solved our problem. Well, not really. If you think deeply, what does this do? This is a load manager. How does it decide which request will go to which of these servers? That is an interesting question to answer. So let's understand that. So let's say I come up with an algorithm which decides which request goes to which of these servers right here. Let's say the algorithm works in this fashion. The first request goes to server 1. The second request goes to server 2. The third request goes to server 3. Fourth request comes in and then it goes to server 1 again. Fifth request comes in, goes to server 2. And sixth one goes to server 3. You see the trend here? It's like a round robin style of distributing the load. We rotate between these servers. First, second, third, then again first, second, third, then again first, second, third, and it goes on. This is a very common style called as round robin. So if we do that, the common distribution that we see here is that around 33k request goes to server 1, around 33k goes to server 2, and similarly around 33k goes to server 3. So it's equal distribution, right? Everything looks perfect. We have devised a very simple formula to this and it's very easy to do. Now let's say this 100k requests are too much for these 3 servers. Now what will happen? In this case, we'll add another server called as server 4. And we'll need to redistribute the load on each of these servers. So let's say 8k requests from server 1 get transferred to server 4. Similarly, 8k requests from server 2 get transferred to server 4. And the same thing for server 3 to server 4. So now after all of this, each of these servers have 25k requests being served by them. Easy, right? Now this is where the problem arises. If you see, the total number of users disrupted is equal to 8k plus 8k plus 8k, which is 24,000 users get disrupted when a new server is added, which is too much. Now there is one more problem if you look closely. Let's say the user 1 and 4 was being served by server 1 that you see here. Now after adding server 4, 8k requests got transferred to server 4. Let's say the fourth request or the fourth user was transferred from server 1 to server 4. And also let us assume that fifth user got transferred to server 4 as well from server 2. Now in this case, how does load manager know that the fourth user is being served by server 4 and fifth one is also served by server 4? It will need to somehow keep a track of which of the requests or the users are being served by which of the servers, right? So we'll need some kind of a mapping right here in the load manager. So let me just add that here in the diagram. So now we have a mapping between which of the user ID is being served by which server ID in this load manager. Well, looks like we have solved the problem now. Not really. We get into some new problems now. These are some problems that we get into. First of all, if we have some kind of mapping right here, this will become a single point of failure. Now, what does single point of failure mean? That basically means that if this load manager fails, then our system just crashes. We can't do anything. So that is the first problem that we get into. But let's say we can solve that problem by having multiple load managers. Okay, now let's move on to the second problem. The second problem is basically the efficiency problem. for deciding on which user is being served by which server, it needs to look for that mapping in the memory, and looking in a memory is pretty slow. So it's a less efficient solution. And here we have just 100k requests. Let's say there are millions of requests. Just imagine how slow it would be. So we need to have a solution where we don't have to look up inside a memory. And that brings us to the third problem, which is this whole algorithm is hard to scale. Now let's understand another scenario also. Let's say we have this load manager right here. It's taking in 100k requests and dividing between server 1, 2 and 3. All of a sudden, server 2 crashes. In this case, all of the 33k requests that was being served by server 2 needs to be distributed between server 1 and server 3. Let's say 17k requests goes to server 1 and 17k requests needs to go to server 3. So the total number of users disrupted is 34k. And that number is a lot. So as we saw, when there was no addition of servers or there was no crash, this algorithm worked perfectly, just like a charm. But when we add new servers or remove the older servers due to a crash, this algorithm fails. And that is where consistent hashing comes in. So let's understand that next. Now let's understand consistent hashing. So in order to understand that, let's take some assumptions. Let's say the request IDs that we get are 1, 2, 3 and so on. And we have assigned IDs for servers too, which are 1, 2 and 3 and so on. For this example, we'll take only 1, 2 and 3, only 3 servers. So what happens in this consistent hashing? You see the circle right here? What we do is use a hash function for requests and use a hash function for servers. They are different. The request hash function is h0x and server hash function is h1x. So what happens is that when a request comes in, we calculate the h0x of the request ID, and then what we do is do a modulo operator on some value. In this case, I have just taken 13 as an example. So we calculate that for each of the requests. Similarly, we calculate that for all of the servers. So as you can see, when we calculated this for server 1, the value came out to be 2, and that is why it's placed in the second spot. Similarly, we did it for second server and it was placed at number 6. We calculated h03, which is the value for the third server, and then a modulo operator on 13, which gave us 10. Similarly, we did it for all of the request IDs. You see 1, 2, 3, 4, 5, 6, 7 just landing around this ring. We calculated for all of those request IDs using the hash function h1x and then did a modulo operator on 13. That's how we got all of the requests and the servers mapped to this circle. Now we talked about the algorithm part, but why did we do it? This mainly because we want equal distribution of these requests onto the servers, right? That is the ideal scenario. They basically distribute all of these requests onto these different servers. In an ideal scenario, it will be an equal distribution. So let's say there are 9 requests, those will be equally distributed between these 3 servers. So let's say for convention, all of the requests are being served by a server which is ahead of them clockwise. So what does that mean? That means that, for example, let's say for 12, it will be served by the second. It will be served by the server number 1. For 6, what is ahead of it? Server 1. For 1, it is server 1. For 7, S2 is ahead of it in a clockwise direction, and for 2, it is S2. Similarly, these will be served by S3. So that is the convention we'll follow. Now, do you think this will solve the problem? Well, in order to answer that, we'll need to add or remove servers. So let's just see what happens in this case. So let's say we add a new server. Let's say it's S4. Now what happens in that case? You see this 5th request right here? That gets transferred to S4. So earlier S1 used to handle 3 requests, now it handles 2. So there is a 33% decrease, and S4 handles 1 request. This seems to solve the problem, right? We are able to add servers elegantly and the load is being distributed. But what happens if we have a crash in one of these servers? Let's understand that now. Let's say server number 1 crashes. In that case, all of these requests, request number 1, 6 and 5, which were being served by S1, will now be served by S2. And the total load on S2 was previously 2, is now 5, which is more than double, and it's a huge issue for S2. Almost half or even more than half of the requests are being served by S2 now. Ideally, what should have happened here? Pause the video here and think about it. How would you handle this problem elegantly? So ideally what would happen is the load that we see here for request 5, 6 and 1 should have been equally distributed to S2 and S3, but it got transferred to only S2. So we need to devise an algorithm in such a manner that whenever a new server comes in, load from all of the rest of the servers get transferred to the new server equally. And when a crash happens in one of the servers, that whole load from that server gets equally transferred to other servers. That's what we want to achieve. So now let's look at the complete algorithm, which is an improvement on this one. So this is what we do here. You see the server hash function? Now we have multiple server hash functions. Let's say h1x, h2x, h3x, there could be more. Now what does these server hash function mean? Earlier we only had h1x and we did a modulo on 13 and we mapped it to this ring here, this circle. We got different spots for S1, S2 and S3. You see these previous ones? Now we have another hash function h2x. So you see these new additions of S1, S2 and S3 in the diagram? These are a result of h2. So the whole idea is that we'll have multiple spots for these servers. So in this case, S1 will have 2 spots in this circle. S2 will have 2 and S3 will have 2 again. Now if you look at any of these requests, let's take a look. So number 1 request is being served by S1. Number 6 is being served by S2. Number 5 is being served by again S1. Number 4 is being served by S3. Number 3 is also being served by S3 because S3 comes after 3. Similarly, 2 is being served by S3 here. 7 is being served by S3 here. And S2 doesn't get anything. So the total load on S1 is this 1 and this 5, which is 2. The total load on S2 is 1 right here and here nothing. So that is 1. And the total load on S3 is 1 and 2 here and 1 and 2 here. So that is 4. Well, not equal distribution in this case, but usually we see an equal distribution. Now this looks good for now. So let's just check this whole algorithm when a new server gets added. What happens in that case? Let's say, so here we have added a new server called as S4. Now what happens in this case? So let's take a look. 1 is being served by S1. 5 is being served by S1. So total load on S1 is 2. 6 is being served by S2. And that's the overall load for S2. 4 is being served by S3 and 2 is being served by S3. So total load here is 2. 7 is being served by S4 and 3 is being served by S4. So 2. So you can see it's a very good distribution, almost equal distribution. So with this algorithm, we are able to add new servers and the load is being distributed equally. Just a reminder, for mapping the values, for finding the spots for these S4s, I used H1x and H2x to find those values. Just how I did it for S1, S2 and S3s. So if a new server comes in, we'll calculate these values H1x and H2x and then map them to this circle. So adding a new server looks good now. Let's now move on to removing the servers. Now let's assume that there is a crash on the server number 3. What happens in that case? So as we saw earlier, the ideal scenario should have been that if let's say S3 had a load of 4, those 4 users get transferred to rest of the servers equally. That would be the ideal scenario. Now let's see with our updated algorithm, would it distribute things equally from the crashed servers? So let's say S3 got crashed. Now you see the request number 4 that got transferred to S1. Request number 3 got transferred to S1. Request number 7 got transferred to S2. And request number 2 got transferred to S2. Now let's calculate the overall load. Now S1 at this spot is handling 3. So the load is 3. Request number 3, 4 and 5. And it is also handling the request number 1. So total load on S1 is 4. Now let's calculate that for S2. S2 handles request number 2 and 7 here, and it also handles request number 6. So total load on S2 is 3. You see, the distribution is still equal. So that says that this algorithm of consistent hashing is distributing the load equally to rest of the servers even if there is a crash. And that's the magic of consistent hashing.